Let's talk about how to determine the chemical formula. The percent composition of a compound is the mass percentage of each element in the compound. We define the mass percentage of, say, A as the parts of A per 100 parts of the total by mass. That is, mass percent of A is equal to the mass of A in the whole divided by the mass of the whole times 100%. So basically this is the fraction of the sample that consists of A. If you're given the percent A by mass, it is useful to put the percentage in a ratio form for dimensional analysis calculations. So if I'm given, say, for example, 20% A, I can rewrite that in a ratio. That way I can continue to do my dimensional analysis. So 20% A is really telling me I have 20 grams of A per every 100 grams of sample. Let's calculate the percent composition, meaning the percent carbon, percent hydrogen in one molecule of butane. So just one molecule of butane, C4H10. First, we need the molecular weight of C4H10. We know how to do that. We've got 4 carbons at 12.01 AMUs per atom, which is 48.04 AMUs. 10 hydrogens at 1.01 each is 10.10 AMUs. It gives me a total mass of one molecule of C4H10 having 58.14 AMUs. That's for one molecule. Now, if I want to figure out the percent carbon and hydrogen, I just take the amount of carbon I have and divide that by the total mass, and I do the same thing for hydrogen. So now, the percent carbon would be my 48.04 AMUs of carbon. That's what's contributing to the total. Divided by the total, 58.14, times 100%, gives me 82.63% carbon. Now a caution here is that percent sign. That is a unit like grams, liters, etc. That's not the percent on your calculator. Okay, so that's a unit. So I'm going 48.04 divided by 58.14 times 100 in my calculator. And then I'm putting percent behind it for my final answer. Do the same thing for hydrogen. We know we have 10.10 contributing to the whole. Divide that by the 58.14 times 100 gives me 17.34% hydrogen. Now this is the amount of percent carbon and hydrogen for one molecule of C4H10. Now how would that differ if I wanted it for 1 mole of butane? Well, if you recall the law of definite proportions, the answer should be it doesn't. It should be exactly the same. If I have 1 molecule or mole of that, it's still going to be 82.63% carbon and 17.37% hydrogen. The main difference is that we'll be doing, instead of AMUs, we'll be having grams in our calculations. But it still mathematically will still be the same numeric numbers, 82.63% carbon and 17.37% hydrogen, based on the law of definite proportion. Let's do a calculation. How many grams of carbon are there in 83.5 grams of formaldehyde, CH2O? And we know that it has 40% carbon, 6.73% hydrogen, and 53.3% oxygen. Now in this particular problem, we're only looking for the amount of carbon. We don't really care about the hydrogen and oxygen, but we could do the same calculation we're about to do for carbon for hydrogen and oxygen if the question required it. First thing you want to do here is we want to get this in terms that we can do our dimensional analysis. We need to think about that 40.0% carbon and how can I rewrite that in a ratio form? Well, we said that we can take that and rewrite it as 40.0 grams of carbon per every 100 grams of sample of formaldehyde. So what I'm basically going to do now is take my 83.5 grams and convert that grams, okay, of the sample of formaldehyde into grams of just carbon. So I'll start off with my 83.5 grams of my sample, formaldehyde, multiply that by my ratio. In this case, my grams of formaldehyde is going to be in the denominator for I can get it to cancel. So my grams cancel of my sample, my formaldehyde, which then gets me my final answer of 33.4 grams of carbon. As I stated earlier, we could do the same calculation with the hydrogen and oxygen if we wanted to figure out how many grams of each one of those species was involved as well. And also, say I wanted to do all three, if I did the hydrogen next, I could figure out its grams. I could take that grams, take the grams of my carbon, add those two, and subtract that from my total gram of the sample, the 83.5, and determine the oxygen that way as well, and that go through the entire calculation of the ratio. Let's look at this problem, a little bit more complex. I got an unknown acid that contains only carbon, hydrogen, and oxygen. I have a 4.24 milligram sample of acid that's completely burned. It gives 6.21 milligrams of CO2 and 2.54 milligrams of water. What is the mass percent of each element in the unknown acid? So we need to figure out what are we actually looking for. Well, the goal of the problem is the percent carbon, hydrogen, and oxygen in the sample. In essence, I'm looking for how many milligrams of carbon, hydrogen, and oxygen we have. Get those values, divide by 4.24 milligrams of sample, times 100% to figure out that percent. So we have an unknown acid that has carbon, hydrogen, and oxygen. In fact, 4.24 milligrams. We're burning that into some oxygen, and we form CO2 and water, which we can measure and find out that we have 6.21 grams of milligrams of CO2 and 2.54 milligrams of water. Now notice that all the carbon of my sample is ending up in CO2. All the hydrogen in my sample is ending up in H2O. However, that's not the case for the oxygen. All that oxygen is forming in that CO2 and H2O, but I also, not only do I have oxygen contributing to these two species, I also have oxygen coming from the combustion as well. So I cannot do the oxygen as a straight calculation. However, there's ways to get around that. One way, if I can figure out the carbon and hydrogen, I know that the total equals 100%. I can subtract those two from 100 and give me my oxygen as well. And there's a few other ways we could do it. So, what we're going to do is start off with our carbon, and let's figure out how much carbon there is in milligrams from this combustion. So I'll start off with my 6.21 milligrams of CO2 because all my carbon from my unknown acid is now in the form of CO2 after this combustion is complete. Now, my goal here is to get to milligrams of carbon, so I go through CO2 to carbon. So anytime I go between a substance or through species, I always do something that's called the mole-to-mole ratio. So I got to get from my CO2 into moles of CO2. And once I'm there, I can look at the substance of CO2 and see for every one CO2 I have one carbon. I also have two oxygens, okay, but I'm not using that in this particular problem. So I'm going to first convert this from milligrams to grams before I can use my molar mass, which is a gram to mole ratio. So I have my milligrams, they cancel, and then I go from my moles of CO2 to grams of CO2 through my molar mass. This is my molar mass of CO2. You see my milligrams are canceling, my grams are canceling. So that gets me in my moles of CO2. And to get from CO2 to C, this is my bridge. Anytime I go from one species to the other, I go through mole to moles. I know for every one CO2, I have how many C's? 1. Okay, so I got a 1-to-1 mole ratio between my CO2 and carbon. So I can plug that in. So I have 1 mole of carbon to every 1 mole of CO2. All right, that's how we convert from one species to the other. You can see my moles cancel, so now I'm in moles of C. Well, how do I get from moles of C to grams of C? Molar mass again. So this is my molar mass of my carbon. We know there's 12.01 grams of carbon for every 1 mole of carbon. Once again, my moles cancel. Now, our goal is milligrams of our carbon, so I have to go back to milligrams. So then I have 1,000 milligrams for every 1 gram. which then gets me to my milligrams of carbon, 1.69 milligrams of carbon. Now notice in this problem that I had to divide by 1,000 and multiply by 1,000. So it's one of those things that we talked about earlier. I can get around this by doing it by prefixes and thinking about that milligrams as basically milli as a separate part of that unit. And say, okay, let's do our molar mass. Instead of doing it moles per gram, I can do the same thing to the numerator as the denominator. Call it millimoles per milligrams. And I can simplify my calculation and avoid that 1,000 dividing and that multiplying by 1,000. This is how we're going to handle the hydrogen part of this problem. So I'll start off with my 2.54 milligrams of water, because we know all our hydrogen from the unknown acid is now in the form of water. So instead of doing the milligrams grams, I'm going to do my molar mass next. Okay, but instead of doing it as moles per grams, I'm going to do it milligrams per millimole. Okay, same procedure as before, my molar mass. This is molar mass. However, I got that milli part added to my grams per mole. Therefore, my milligrams cancel. Now I'm in millimoles. I got to now get from water to hydrogen, so I'm going to do my mole to mole ratio again. In this case, you can see for every one of my H2Os, I have 2 hydrogens. Okay, so we'll do our ratio, but instead of mole to mole, I'm going to do millimole to millimole. So I got 1 millimole of water to 2 millimoles of hydrogen, so my millimoles cancel. Now I want to get back to grams, so I'm going to do molar mass again, except in this case, I'm going to do it in milligrams per millimole. So I get 1.01 milligrams of hydrogen per 1 millimole of hydrogen. So my millimoles cancel again. Now I'm in milligrams, so I'll figure out my milligrams of hydrogen. 0.285 milligrams of hydrogen. And notice the same calculation to carbon and hydrogen, except we kind of avoided that 1,000 situation by doing the millimole aspect of it by thinking about that prefix. Now, I got to figure out oxygen. There's a couple of ways. Okay, the simplest way is to say, okay, I know that my unknown sample was 4.24 milligrams, and I already know the amount of carbon and hydrogen. Well, anything left will tell me how much oxygen was present. So we'll do that calculation. So for oxygen, we're just going to take the total mass, which is 4.24 milligrams. That's going to equal the mass of the carbon, the mass of the hydrogen, and the mass of the oxygen. Plug in my numbers I found out for carbon and hydrogen, subtract those numbers, and that will give me my mass of oxygen. So 2.26 milligrams of oxygen was part of that unknown acid. Now, if I was to figure out the amount of oxygen from CO2 and H2O, I could do that. The problem is going to be that it's going to be greater than that 2.26 because I had some oxygen coming from that combustion. And there's ways to figure out how much that is and subtract it, but this is the easiest way to go by. So now I want the percent carbon. So that's going back to our formula, which is your milligrams of your species divided by the total milligrams of sample times 100%. So in this case, 1.69 milligrams of carbon divided by 4.24 milligrams of sample times 100%, where the percent is a unit, not the percent on your calculator. It tells me I got 39.9% carbon. Now we did it in milligrams. We could have did it in grams, converted the milligrams to grams, and then kept it in grams for carbon, and it still work out the same. Percent hydrogen. Plug in those numbers, 0.285 milligrams of hydrogen over the total, 4.24 milligrams, times 100, gives me 6.72% hydrogen. Oxygen, well, once again, we can simplify this and find the percent oxygen instead of doing the whole calculation of percent oxygen. I know that the totals have to equal to 100%, so I can, from 100%, subtract my 39.9% and my 6.72%, and what's left will tell me my percent oxygen. Okay? Or I could plug it in to the equation directly, as I got typed right here. 2.26 milligrams divided by the 4.24 times 100 gives me 53.4%. As I said, alternatively, the easier way would have been to do this. Take my 100% minus the 39.9 minus the 6.72% tells me I got 53.4% oxygen. Now we can determine the formula of a compound from the percent composition. We can determine the percent by doing several experiments to isolate the components and get the percent of each element involved. The percent composition of a compound leads directly to its empirical formula. The empirical formula, or the simplest formula for a compound, is the formula for the substance written with the smallest integer whole number subscripts. From this we can find the molecular formula of the substance, which will be some multiple of the empirical formula based on its molar mass. For example, benzoic acid, it's a white crystalline powder used as a food preservative. The compound contains 68.8% carbon, 5% hydrogen, and 26.2% oxygen by mass. What is the empirical formula? In other words, we want to find out the smallest whole number ratio of the subscripts in the formula based on moles. How many carbons there are to hydrogens and hydrogens to oxygen. So we're looking for the formula, C, X, H, Y, O, Z, where we're trying to find out what is X, Y, and Z. And these things are based on moles. For the purposes of the calculations of this type, we will assume that we have a 100-gram sample. This we can do anytime we do a calculation. This just to make life easier to figure out how many grams of each substance we have. Therefore, for benzoic acid, if we say it's 68.8% carbon, and we assume a 100-gram sample, then we basically have a 100-gram sample, got 68.8 grams per 100-gram sample, tells us our gram samples cancel, tells us I got 68.8 grams of carbon. So anytime I can just assume a 100-gram basis, and that percent actually tells me the grams I got before I can do the rest of my calculation. Which means the mass of each element equals the numeric value of the percentage. Since X, Y, and Z in our formula represent mole-to-mole ratios, we must take this mass and convert it to moles. So based on our assumed 100-gram sample, and our percentages of carbon, hydrogen, and oxygen, we can do the calculation. And we know that if I have 68.8 grams of carbon, using the molar mass of carbon, I can figure out the moles of carbon. Hydrogen, got 1.01 grams per mole, molar mass, tells me my moles of hydrogen. 26.2 grams of oxygen, 1 mole to 16 grams of oxygen, 1.63 moles of oxygen. Note that the masses add up to 100 grams. That's because we assumed a 100-gram sample. We could have did 1 gram. We could have did 1,000 grams, 1,050. Doesn't matter. It's a percentage, and you can calculate it. However, the simplest thing is just do a 100-gram basis, and there's no calculations involved. Now, this isn't quite a whole number ratio. We're saying I got 5.72 carbons for every 4.9 hydrogens to every 1.63 oxygens. So we need to get this all on the same basis. Okay, so if we divide each number by the smallest of the three, we can get a better ratio that will emerge that we can figure this out. So we are dividing by the smallest number to get the species all on the same scale. Basically, we normalizing the values. So the next step is to get all species on the same scale. Basically normalizing to moles of the smallest species. In this case, 1.63 moles of oxygen, for the purpose of getting values that can easily be converted to whole number ratios. So I have 1.63 moles of oxygen, divide that by 1.63 itself, the same number, tells me I'm going to get that down to 1. So one species is going to be 1. I'm going to get it down to the smallest one. Then we take the carbon, the 5.72, and divide that by 1.63, and we get 3.50 rather. Then I get 4.95 moles of hydrogen, divide that by that smallest number, which is 1.63, gives me 3.0. So in essence, we know the ratio of moles now is 3.5 carbon to 3 hydrogens to 1 oxygen. Now we want a whole number ratio, so I need to multiply these factors by some number. We can easily see that I can multiply everything by 2 to get rid of that half. Okay, I want to get that to a whole number, so if I multiply everything by 2, I can get some whole numbers. So it's not difficult to see that the smallest whole number ratio is a 7 to 6 to 2. I multiply everything by 2. 2 times 3.5 gives me 7. 2 times 3 gives me 6. And 2 times 1 gives me 2. So the empirical formula is C7H6O2. Now it just so happens for benzoic acid, the empirical formula and the molecular formula are the same, because the molar mass of my empirical formula and the molar mass of my molecular formula are exactly the same value. Now what happens if that's not the case? We have to look at an example of that. An empirical formula gives only the smallest whole number ratio of atoms in a formula. The molecular formula should be a multiple of the empirical formula, since both have the same percent composition. If it's 60% carbon and 40% hydrogen, it doesn't matter if it's empirical or molecular, it's still going to be the same percentages because it's law of definite proportions. So I'm going to have to calculate how many times that the empirical formula is divisible into that molecular formula to figure out what is the actual molecular formula. So if I have an empirical formula, say C2H3O2, those numbers have to be the lowest whole number ratio. Basically, they cannot be divisible by any number. We've got odds and evens here, so it's not. If I had something like C4H6O4, you can see that's divisible by 2. So that's not an empirical formula. That's a molecular formula. So that's twice the empirical formula above. Another example, C8H12O8. That's a molecular formula. That's a multiple of 4 times the empirical formula. So basically, I'm multiplying that empirical formula by 4 to get my 8, 12, and 8. Okay? So if I knew the molecular mass of my molecular formula, I knew the empirical formula mass, I can figure out how many multiples it is from that empirical to the molecular formula. Let's make sure we understand what an empirical formula is, okay? Which is not an empirical formula, meaning not the lowest whole number ratio. Well, look at CH4. That's not divisible by anything. I got a 1 and a 4, so that's fine. Is CH4O an empirical formula? Yes, that's all lowest whole number ratio. It's not divisible by anything. What about C2H4O2? That's all even numbers. That's divisible by 2. So that's not an empirical formula. So that's not one. This is a molecular formula. What about C2H6O? Nope, that's not divisible by anything. So therefore, that's an empirical formula. So C2H4O2 is divisible by 2. Therefore, CH2O would be the empirical formula for C2H4O2. To determine the molecular formula, we must know the molecular weight or molar mass of a compound. Determining the molecular formula from an empirical formula requires the following equation. You know your molar mass. It's equal to N, where it's the multiple factor, time the empirical formula mass. Or rearranging this. You can determine the molecular factor by dividing the molar mass of the molecular equation divided by the empirical mass of the empirical formula. So, let's demonstrate this in a problem. Acetic acid contains 39.9% carbon, 6.7% hydrogen, 53.4% oxygen. Determine the empirical formula. That's the first part of this problem. Second part is, the molecular mass of acetic acid is 60.0 grams per mole. What is the molecular formula? Now, we did this with benzoic acid, but the molecular mass and the empirical mass ended up being the same value. In this problem, it's not going to be. That molecular mass is going to be some multiple of the empirical formula. We will determine the N and figure out what is the molecular formula. So we'll handle this the same way we did just recently. We're going to assume a 100-gram sample, meaning we have 39.9 grams of carbon, 6.7 grams of hydrogen, and 53.4 grams of oxygen. We will calculate the moles of each because it's a mole-to-mole ratio on that formula. So I got 39.9 grams carbon. Molar mass, 12.01 grams. Tells me I got 3.33 moles of carbon. Hydrogen, molar mass, 6.6 moles of hydrogen. 53.4 grams of oxygen. So 1.0 moles divided by my 16.0 gives me 3.33 moles of oxygen. Notice all my units are canceling, leaving me in moles. So now I know the ratio of carbon, hydrogen, and oxygen. It's a 3.33 to 6.6 to a 3.33 ratio. We need to get this all on the same scale, so we're going to divide by the smallest number, which happens to be the same one for two of them. So if we do that now, we're going to divide everything by the smallest number of moles of 3.33. So the first one will end up being 1 carbon. 6.6 divided by 3.3 will give me 2 hydrogens. And 3.3 divided by 3.3 will give me 1 oxygen. So the empirical formula is CH2O. That's my empirical. Now if I add up the molar mass of that, 1 carbon, 2 hydrogens, and 1 oxygen, let's see what we get. We get a molar mass of 30.03 grams per mole. Now that does not equal the same molar mass of our molecular substance of acetic acid. So we need to figure out how many multiples that formula is of the empirical formula. Well, that goes back to our equation of N is equal to your molar mass divided by your empirical mass. We were given that 60 grams per mole is the molecular mass of our acetic acid, and the empirical mass we calculated was 30.03. If I divide that, I find out how many multiples it is of that empirical formula to get to my molecular formula, which is, in this case, 2. So I'll take my CH2O, multiply it times 2. So I'll multiply my carbon by 2, my hydrogen by 2, and my oxygen by 2, which then gives me my final molecular formula for acetic acid is C2H4O2. Homework 23.